Imagine you are an architect. You have spent the better part of a century constructing a blueprint. Not a blueprint for a building or a bridge, but for everything. A technical drawing of reality itself. From the first second after the universe was born to the sprawling web of galaxies that fills the sky tonight. This blueprint is called the Standard Model of Cosmology, and it's a masterpiece by almost any measure. It revealed, almost with unsettling precision, that everything we can see and touch, from the atoms in your body to the stars scattered across the sky, makes up a mere 5% of the universe. Imagine a room filled from floor to ceiling with every kind of matter the universe has ever produced. Yet the only part you can touch, see, or feel is a single small shelf in the corner. The rest lies hidden in darkness. That unseen majority mirrors our universe. Dark matter is invisible, cold and slow-moving, spread throughout space like an unseen skeleton holding everything together. Dark energy, by contrast, is not matter at all, but a property of space itself, quietly driving the universe to expand faster and faster. So what we experience, the small shelf, is only a tiny fraction of what truly exists. Cosmologists told us where galaxies would form, how they would cluster, and what the large-scale architecture of the cosmos would look like. The great cosmic web of filaments and voids that stretches across billions of light years. And when they tested their predictions against the sky, the universe answered back almost perfectly. For decades, the observations matched what they expected to see. We thought the framework was settled. We were wrong. In 2021, the James Webb Space Telescope launched from the Guyana Space Center on a rocket into the night sky. It was a machine unlike anything humanity had ever built. A gold-plated mirror 6.5 meters across, folded like origami, designed to peer so deep into space and so far back in time that we could watch galaxies being born. The first hints that the model was wrong came in the form of strange galaxies, appearing too early or too bright for the age of the universe they inhabited. Then came the little red dots, compact and intensely luminous objects that the standard model struggled to explain. And then came a discovery that would quietly shake the foundations. Researchers studying the shapes of early galaxies found something the model did not predict. According to the standard model, the invisible skeleton of cold, dark matter, those slow-moving particles that clump under their own gravity, should force young galaxies to form inside roughly spherical halos, like pearls forming around grains of sand. But the galaxies Webb found were not spheres, but elongated. Astronomers called them prolate, a technical term for a shape closer to a rugby ball than a beach ball. They looked like cosmic cigars. Galaxy after galaxy, Webb kept insisting on the same stubborn shape, not the spheres the model promised. To understand why the shape of a distant galaxy matters so much, you have to understand the role that dark matter plays in our model. It is the scaffolding. In the standard model, cold dark matter is cold in a very specific sense. Its particles move slowly relative to the speed of light. Because they move slowly, they can clump together under gravity at small scales, which help to form dense, roughly spherical halos. And it is inside those halos that gas falls and cools, which eventually collapses into the first galaxies. The shape of the dark matter halo imprints itself on the galaxy that forms inside it. A spherical halo will turn into a spherical galaxy. The problem with this is that the galaxies are not spherical. They are cigars. Here is what makes this finding genuinely alarming to the field. Those cigar shapes are not random noise. They are not a prediction of cold dark matter. 2. Alternative models called warm dark matter and wave dark matter describe dark matter particles that are either lighter or quantum mechanical in ways that produce fundamentally different behavior at small scales. Warm dark matter is the simpler revision. Its particles are just faster, and that extra speed stops them from clumping as tightly at small scales. Wave dark matter is stranger. Its particles are so light, they stop behaving like particles altogether, smearing out into vast quantum waves that can span entire galaxies. Instead of clumping into tight spherical halos, these alternative models produce long and flowing streams of matter that stretch across millions of light years, like rivers carved into the fabric of space. And when gas and stars form inside these, they do not collapse into spheres. They slide along the stream and stretch into the shape the stream already has. The moment a scientist considers replacing cold dark matter with one of these alternatives, they step onto treacherous ground. Because this is not a peripheral assumption you can revise quietly without disturbing the rest of the structure. It is woven into every prediction the Standard Model makes about the cosmos. If you change the nature of dark matter by, for example, making it warmer, the ripples from that change will bleed through everything. The distribution of galaxies across the sky would alter. The predicted mass of galaxy clusters would need to be recalculated. And the maps we have drawn of the large-scale structure of the universe, painstakingly assembled from millions of galaxy observations, would need to be redrawn. This is what physicists mean when they talk about a crisis rather than a problem. A crisis is a question whose every possible answer breaks something you were relying on, and the cigar shapes are not the only crack. For nearly a decade, two independent ways of measuring how fast the universe is expanding have given two stubbornly different answers. It's a discrepancy so statistically unlikely, it would be like flipping a coin and getting heads 3.5 million times in a row. It is called the Hubble tension, and Webb has so far deepened the mystery rather than resolving it. So the model is fracturing in more than one place, and the response from the scientific community has not been silent. It has been a fight. Some researchers are trying to save cold dark matter. They argue that the cigar shapes could be explained without abandoning it entirely, that violent feedback from supernova and supermassive black holes in the early universe could have reshaped galaxies after they formed, stretching spheres into elongated structures through sheer brute force. Others point to mergers, early galaxies colliding and fusing along preferred directions, which produce elongated remnants that only look like they formed inside filaments. These are not just random arguments. They come from groups with decades of simulation work behind them, and they are defending a model that has earned its place. But the defenders have a problem. The cigar shapes are not appearing in one or two galaxies that could be dismissed as outliers. They are appearing consistently across a wide range of early galaxies, at a rate that CDM simulations do not reproduce even when feedback and mergers are accounted for. The pattern is too widespread to be explained away as a side effect of something else. And on the other side, the supporters of warm and wave. Dark matter are cautious too. Their models predict the filaments and elongation, but they also predict other things, like fewer dwarf galaxies and smoother density profiles. Things that have not yet been conclusively confirmed or ruled out. Nobody is declaring victory, as everybody knows that the next round of observations could vindicate their model or destroy it. What you are watching is science at its most honest and most uncomfortable. A field full of brilliant people who built something extraordinary, staring at evidence that it might not be enough. You cannot swap out the foundation of a building and expect the walls to stay where they are. If you made it this far, you're the kind of person this channel is for. Subscribe so you don't miss what comes next. It is not panic or despair. It is something more specific than that. It is the feeling a scientist gets when they find a puzzle piece that does not fit the box, and then look more carefully at the picture on the box and begin to suspect that the picture might be wrong. It is the recognition that what feels like a flaw in the data is actually a door. The history of physics is full of these moments. The perihelion of Mercury did not fit Newtonian gravity, and the discomfort of that discrepancy was the door that opened onto general relativity. The universe did not behave the way Einstein expected when he applied his own equations to it, so he invented the cosmological constant. And decades later, the evidence for dark energy vindicated like that instinct, though not in the way he imagined. Every one of them turned out to be a map correction, and the new version was stranger and more beautiful than anything the previous generation had drawn. The galaxies Webb found, the little red dots, the prolate structures that look nothing like what cold dark matter predicts, these are not embarrassments. They are the universe refusing to fit the box we built for it, telling us that we have been drawing the map from incomplete information, and that the actual territory is richer than our model has room for. We are a species on a small rocky planet, orbiting an unremarkable star in the outer arm of a galaxy, among hundreds of billions of galaxies. And we are arguing, with genuine rigor and legitimate mathematics, about the shape of invisible matter that existed billions of light years away far before our time. We are doing this with mirrors and math, with a telescope that had to unfold itself in space in a sequence of 344 individual steps, any one of which could have ended the mission. We are doing this by measuring the way light pulses from dying stars, by mapping the faint temperature variations in light that has been traveling since the universe was barely an infant. And yet, here we are, genuinely unsure whether the particles we have never detected are cold or warm or quantum mechanical in ways our current equations do not capture, genuinely living inside a question. The standard model of cosmology is not broken, but it is for the first time in a long time, visibly and uncomfortably incomplete. The fractures are real, and so are the cigar-shaped galaxies. Something is missing. Every map in history has eventually been superseded. The maps that showed the world's coastlines trailing off into blank space were not wrong. They were incomplete. Cosmology is standing at one of those edges right now. The Euclid Space Telescope, launched in 2023, is in the process of mapping the three-dimensional distribution of galaxies across a vast swathe of the sky, building a census of the cosmic web that will test both the Hubble tension and the predictions of alternative dark matter models simultaneously. And Webb itself continues to look. Each observation cycle brings new data, new galaxy shapes, new objects that do not quite fit the expected pattern. The next version of the map is being drawn right now. We do not know yet whether it will require a modest revision or a fundamental rethinking. We do not know whether warm dark matter or wave dark matter will survive the scrutiny of the next decade's observations. We do not know whether the Hubble tension will resolve into a mundane systematic error in the measurements or crystallize into something genuinely revolutionary. But we do know this. The question is alive, and the puzzle piece does not fit. The universe is not broken. It is simply larger than our current imagination, more intricate and more surprising than any single model has yet managed to contain. And somewhere in the space between what we predicted and what the telescope found, in the gap between the sphere we expected and the cigar we observed, in the 6 kilometers per second that separate two measurements of the same expanding cosmos, somewhere in that gap, the next version of the truth is waiting to be found. We just have to be willing to look.